Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Level 102, determine the x-coordinate of the centroid of the volume shown. So we have the hint here. The height y of the volume is proportional to the x-coordinate. Consider an analogy between this height and the water pressure on a submerged surface. So I'll present two ways or two solutions for this problem. One is by considering the miscellaneous solid and finding the location of the x-coordinate of the centroid. The second one is to use this hint here. So here is the given figure. So we let's consider a slab parallel to the YZ plane. So for our solution, that's the slab. The length of the slab along the z-axis is z. Along the y-axis is y also, and the thickness is dx. As shown, the distance of the centroid of the slab from the YZ plane is x, the height is y, and the length is z. And the thickness is dx as shown. So the variable is x. So for this triangle here, this is A and this is B. That is B because we have 2B here minus B, so B. Then this extension here is equal to 2B minus Z. And that distance is of course x. So differential volume is the volume of this slab, of this elemental slab, which is equal to z times y, the area of the rectangle, times thickness dx. And the variable of integration is x, so limits will be from 0 to a. From the figure, y as to x equals h as to a. So y is h over a times x, while uh, 2b minus z as to x equals b as to a. 2b minus z as to x equals b as to a. So 2b minus z equals b over ax. Factoring out b, then we have z equals b quantity 2 minus b over a minus x over a rather. So z is b quantity 2 minus x over a. So that's the value of z. Volume therefore is integral from 0 to a of z, which is b quantity 2 minus x over a, then y h over a times x dx. So volume equals bh over a, integral from 0 to a of 2x minus x squared over a dx. So integrating, volume is bh over a quantity x squared minus x cubed over 3a from 0 to a. So volume equals bh over a quantity a squared minus a cubed over 3a minus substitute lower limit 0. So 1 minus 1/3 is 2/3. Therefore, the volume is 2/3 ABH. So that's the volume of this solid. Then apply Varignon's theorem. Volume times bar x equals integral of x coordinate of the element differential volume. So volume bar x equals integral of x dv, where x is just x because the location of the centroid of this elemental slab from the YZ plane is just x, and differential volume is this expression here. So volume bar x equals integral from 0 to a of x, then b over bh over a quantity 2x minus x squared over a dx. So 2/3 abh bar x equals bh over a integral 0 to a of 2x minus x cubed over a dx. Cancel out bh. So bar x is 3 over 2a squared. Then quantity 2x cubed over 3 minus x to the fourth over 4a from 0 to a. So 2/3 minus 1/4 times 3 halves. So that would be in terms of a, bar x is 3 over 2a squared quantity 2 2/3 a cubed minus a to the fourth over 4a, which is also a cubed, like terms, minus lower limit 0. So solving for barred x is equal to 5 over 8 of a. So that's the answer based on this integral. Then using the hint here, volume is integral of differential volume is integral of, if we denote the differential area on the xz plane, which is z dx, then volume is just equal to y, and we interpret z dx as differential area. So dv is z y dx, so dv is y z dx, and z dx is the area on the xz plane, that's differential area. So dv equals y dA. Therefore, volume or dv equals h over ax, because that's the value of y dA. So volume therefore is h over a integral of x dA. From statics or from integral calculus, this is the first moment of area. Therefore, we replace this by area barred x, or simply qz. Volume therefore equals h over a times q sub z, the first moment of area, or it is equal to area times barred x. So the area, projected area on the xz plane, and the moment of that area with respect to the z-axis or the yz plane. So likewise, for the top view, this is the top view, or the area on the xz plane. So we divide the area into two parts. We have rectangle and triangle. For the rectangle, the area, the dimensions would be a along x and b along z. Then we have this triangle, which is a along x and also b along z. So this is the centroid of the rectangle, that is a over 2. And this is the centroid of the triangle, and this is a over 3. So substitute the value of formula for volume, h over a. Then that is a over 3. H over a, quantity AB times a over 2, the moment of area of rectangle, plus 1/2 AB, then moment arm a over 3 for the triangular part. So remember, this is QZ. So 1/2 plus 1/6 a square b is 2/3. Then 2/3 a square b times h over a, then we get 2/3 abh over 3, which is the same as this. Then likewise, volume times barred x equals integral of x dv, replacing dv by h over a, then x dv dA. So volume barred x equals x times h over ax times dA. Then factor out h over a. Volume barred x equals h over a integral of x squared dA. And this expression, integral of x squared dA, is the second moment of area, this area here, and that is the moment of inertia, because this is the second moment of area with respect to the z-axis. So therefore, we replace this by Iz. Volume barred x equals h over a times Iz. Then from there, barred x therefore is h over a Iz divided by volume, which is h over a qz. So barred x equals h over a Iz over volume, which is h over a qz. Cancel out h over a, so the expression for barred x is moment of inertia of area with respect to the z-axis divided by moment of first moment of area with respect to the z-axis. And take note that we already computed qz. This is qz, a square b over 2 plus a square b over 6. So a square b over 2 plus a square b over 6 is 2/3 a square b. So that's qz, 2/3 a square b from here. Then we need to compute IZ. So IZ is the moment of inertia of this area here, trapezoid with respect to the z-axis. It consists of rectangle and triangle. For the rectangle, it is b a cube over 3 with respect to this edge here. For the triangle, b a cube over 12. Remember, for moment of inertia of a triangle with respect to the base. So IZ is a cube b over 3 plus a cube b over 12, or b a cube over 3 plus b a cube over 12. Combining, that is equal to 5 a cube b over 12. Then substitute here. So 5 Bard x is 5 over 12 a cube b divided by qz 2/3 a cube b. So solving for Bard x, cancel out a square b. So that would be 15 over 24 divided by 3. So that's 5 over 8. So Bard x is indeed 5 over 8 of a. So 5/8 of a. So that's it. And I hope that you appreciate the idea that computing Bard x using this analogy for pressure will give us a very simple expression, because it is just the ratio of the moment of inertia of area with respect to the z-axis divided by the first moment of area with respect to the same axis z. Level 103. Determine the x-coordinate of the centroid of the volume shown. This volume was obtained by intersecting an elliptic cylinder with an oblique plane. So hint, the height y of the volume is proportional to the x-coordinate. Consider an analogy between this height and the water pressure on a submerged surface. So I'll present two solutions again. The first one is using the high-tech calculator in deriving the volume by integration, and second, by this hint here. So consider a rectangular slab for our solution as shown. Then the distance of that slab, centroid of the slab from the YZ plane is x. The height is y. This is z. This is z. So 2z, the length. And the thickness is dx. So call this h. And that distance of the centroid of the slab from the YZ plane is x. And the thickness is dx. So differential volume therefore is 2z by y times dx. So because this is the greater length, greater dimension than 39, so call that a. Therefore, if this is a and that is x, so this distance is a minus x from the center of the elliptic cylinder, and call 39 as b. So a, 39 as b. So dv equals 2zy dx. Then from the figure, y as to x equals h as to 2a. Y as to x equals h as to 2a. A plus a. So y is h over 2a times x. Then the equation of the ellipse with center at a, 0, 0. So it is on the xz plane. So it is x minus a over x minus a quantity square over a square plus z square over b square equals 1. So from review your analytic geometry. So equation of ellipse with center at a 0, 0, or simply a 0 considering the xz plane, is quantity x minus a. This is the x coordinate of the center of the ellipse. Quantity square over a square, semi-major axis square, plus z square over semi-minor axis square equals 1. So from here, z is b square root of 1 minus quantity x minus a square over a square. So z is b square root of 1 minus quantity x minus a square over a square. Substitute into this equation. Volume equals 2 integral of z, which is b square root of 1 minus quantity x minus a square over a square times y, which is h over 2a times x, then dx. Cancel out 2. So volume equals bh over a integral of x square root of 1 minus quantity x minus a, which is 64 square over 64 x dx. So bh over a integral from 0 to 128. The variable of integration, by the way, is x. So it lower limit is 0, then upper limit is here, which is 2 times 64 or 128. So using the high-tech calculator, let's evaluate this part here. Your calculator is allowed. So volume is bh over a, integral 0 to 128 of square root of 1 minus quantity x minus 64 square over 64 square times x dx. And it is equal to 6433.982. So volume equals bh over a times that value. Anyway, bh over a is constant. Uh, you can solve for h is constant. B and A are given constants also. So let's just express the volume in that manner. Likewise, volume times barred x, volume times barred x equals integral of x dv from 0 to 2a or from 0 to 128. dv is interpreted as dv is differential volume is this expression here. So BH over A 6433.982 barred x equals BH over A integral 0 to 128 of x square root of 1 minus quantity x minus 64 square over 64 square times x dx. So cancel BH over A 6433.982 barred x equals integral from 0 to 128 of x square root of 1 minus quantity x minus 64 square over 64 square dx. Again, using your high-tech calculator, you can evaluate this integral, and it is equal to 514718.540. So barred x can now be computed, and it is equal to 80 mm. So that's the solution considering these miscellaneous solids and by integration. Using this analogy, dv is 2zy dx, and we interpret 2z times dx, the differential area on the xz plane, as differential area. So 2 dv is 2zy dx, or dv is y times 2z dx, and 2z dx is differential area. So dv equals y, which is h over 2ax, and we interpret 2z dx as differential area on the xz plane. So since h over 2a is constant, then volume equals h over 2a integral of x dA, and we interpret, or we define this expression as the first moment of area, which is called qz. So volume equals h over 2a times qz, the first moment of area of the ellipse with respect to the z-axis. So likewise, volume times barred x equals integral of x dv, because the x coordinate of the element on this slab is just x, and dv is equal to this. So volume barred x equals integral of x h over 2ax dA. So factoring out h over 2a, so h over 2a qz, which is volume, barred x equals h over 2a integral of x squared dA. Cancel out h over 2a, and we note that integral of x squared dA is the second moment of area, which is the moment of inertia of this projected area on the xz plane, the ellipse, with respect to the z-axis. So h over 2a qz barred x equals h over 2a integral of x over dA, which is iz. Cancel out h over 2a, so barred x is iz over qz. So that we can evaluate iz and qz, let's have the top view of this ellipse here. So in general, this is A, B, B. The moment of inertia of the ellipse with respect to the z-axis is we transfer the moment of inertia with respect to the centroid, which is pi AQB over 4 plus area pi AB, area of ellipse is pi AB times distance A square, while QZ is just area of the ellipse pi AB times distance A with respect to the z-axis. So barred x is pi AQB over 4 plus area pi AB times moment distance square A square. Then moment of area, first moment of area QZ is area of ellipse pi AB times moment arm A. So cancel pi A square B, leaving A only in the numerator. Barred x is in terms of A. 5/4 divided by 1, so 5/4. Therefore, barred x is 5/4 of A. So barred x is 5/4 of A, and A is 64. Therefore, barred x is 80 mm. So that's it for this problem. Level 104 show that the system of hydrostatic forces acting on a submerged plane area A can be reduced to a force P at the centroid C of the area and two couples. The force P is perpendicular to the area and has a magnitude of P equals gamma area barred y sine theta, where gamma is the specific weight of the liquid. The couples are the x component mx prime is gamma I barred x prime sine theta. Then the y prime component is gamma I barred x prime y prime times sine theta, where I barred x prime y prime is the integral of x prime y prime dA. Note that the couples are independent of the depth at which the area is submerged. So here is the given figure. So for our solution, so let's have our differential area somewhere here, and the distance of this differential area along the plane of the area to the liquid surface is y. So that's x and that distance is y, and the angle that y makes with the liquid surface, which is horizontal, is also this angle here, theta, as shown. And the vertical distance of this differential area to the liquid surface is of course y times sine theta. Since differential force P is equal to pressure at this point on differential area times differential area, then by the way, this is the center of pressure, and the distance of the center of pressure from the y-axis is xp or x sub cp, and its vertical distance from the x-axis is y sub cp as shown. So this is y sub cp and this is x sub cp. So likewise, the force differential P acts perpendicular to that differential area. So this distance of this differential area from the y prime axis is x prime, and its distance from the x prime axis is y prime. So differential P is pressure dA, so that's y prime, where pressure is specific weight gamma times vertical distance y sine theta times dA. So dP is gamma times y sine theta, vertical distance, to dA times dA. So putting specific weight and sine theta before the integral sign, then we have P equals gamma sine theta integral of y dA. So with our experience, integral of y dA is equal to the first moment of area, which is area times barred y. So therefore, because P is gamma sine theta area barred y, we have shown that P is really specific weight area barred y sine theta. Then for moment about x prime, so it is supposedly dp times y prime, but we'll not do that yet. We'll simply compute the moment of P about the x-axis first and define moment about x prime later for the couples. So mx equals p times y sub cp. It is by moment of force about the x-axis is p, and its distance, because this is p is acting at the center of pressure. So P is supposedly acting at the center of pressure, and it is equal to P times y sub Cp, and it is equal to integral of y dp. Substituting the value of dp, so this is the differential force and its distance from the x-axis is y, replacing dp by gamma sine theta y dA. So mx equals p y sub cp, and it is also equal to y, and differential p is gamma sine theta dA. Putting gamma sine theta before the integral sign, then we'll have mx equals py sub cp equals gamma sine theta integral of y squared dA. And take note that this expression, integral of y squared dA, is simply the moment of the second moment of area with respect to the x-axis, or simply the moment of inertia of this area here with respect to the x-axis. So we replace that by ix. So mx equals p y sub cp equals gamma sine theta times ix, because this is I sub x. Then because ix is equal to I barred x prime plus area distance square by parallel axis theorem, so mx is gamma sine theta times ix, and ix is I sub c, or I barred x prime plus area barred y square. So moment of inertia with respect to the centroidal axis, which is I barred x prime, or I sub cx plus area distance square, and the distance is parallel distance is barred y, distance between the centroidal axis or centroidal x prime axis and the x-axis is barred y. So that's why we have barred y square here. So gamma sine theta times ix minus area barred y square, because this is ix, so ix minus area barred y prime square is simply I sub c, and I sub c is also I barred x prime. So therefore gamma sine theta ix prime is equal to moment about xx prime, and or moment about this axis here, so that we have shown that mx prime is really gamma times I barred x prime times sine theta. So likewise, moment about the y-axis here is equal to p times x sub cp. So p acting on cp, and moment arm is x sub cp, and it is equal to integral of dp, and the moment arm is x. So this is independent of the depth, by the way, this mx prime here, because in this expression there's no expression here or factor here that is a function of the depth. Ix prime is the property of the area here, so it is not, or it is independent of the depth. Unless barred y is involved in the equation, then it is a function of the depth. So likewise, my equals p times x sub cp integral of x times dp, because the distance of differential area from the y-axis is simply x. So substituting the value of dp, which is equal to gamma sine theta y dA. So my equals px sub cp equals integral of x, then gamma sine theta y dA. Then putting gamma sine theta before the integral sign, so my equals px sub cp equals gamma sine theta integral of xy dA, where integral of xy dA is, because from the figure x is x prime plus barred x, or barred x plus x prime, and y is barred y plus y prime, or y prime plus barred y. So px sub cp equals gamma sine theta integral of quantity x prime plus barred x times quantity y prime plus barred y dA. Now, we only expand integral x prime y prime dA and barred integral of barred x barred y, which are constants, then integral of dA. For the others, integral of x prime barred y dA, the integral of x prime barred y dA, because barred y is constant, so that would be integral of x prime dA. This is x sub c dA, x sub c area, and x sub c is 0 because it means that's the x coordinate of the centroid, which is 0. X is 0 at c. Then integral of barred y, barred x dA is barred x, then integral of y prime dA, integral of y prime dA is area times y sub c, and y sub c again is 0 at the centroid. So therefore, those two terms will be 0. We only consider integral of x prime y prime dA and barred x barred y integral of dA in the expansion. So my equals gamma sine theta integral of x prime y prime dA plus barred x barred y integral of dA. So again, I already explained the reason why the two terms mentioned would be 0, because it will result to y sub c and x sub c as a factor, which are all zeros. So integral of x prime y prime dA is simply I x prime, and of course this one is area barred x barred y. So my equals gamma sine theta quantity I, which is ixy. This is ixy. Gamma sine theta integral of xy dA is ixy. Then gamma equals gamma sine theta. Then this is equal to ix prime y prime. Then plus area barred x barred y. So if we cancel this and put ix prime y prime equals ixy minus area barred x barred y, and the result would be my prime, moment about the centroidal axis, my prime. So gamma sine theta quantity ixy minus area barred x barred y is simply, this one is moment of inertia with respect to the x prime axis, x prime y prime axis, or centroidal x prime y prime axis. So finally, my prime is equal to this. So this is interpreted as my prime. So my prime is equal to gamma sine theta times ix prime y prime. So that's it, which shows here. So my prime equals gamma ix prime y prime sine of theta. And this is also independent of the depth. So that's it for this problem. Level 104, show that the resultant of the hydrostatic forces acting on a submerged plane area A is a force P perpendicular to the area and of magnitude P equals specific gamma area barred y sine theta, or pressure at the centroid of area times area, where gamma is the specific weight of the liquid and P barred is the pressure at the centroid of the area. Show that P is applied at point C sub P called the center of pressure, whose coordinates are x sub P, which is given by Ixy over area barred y, and y sub P, which is equal to Ix over area barred y, where Ixy is integral of xy dA. Show also that the difference of coordinates y sub P minus barred y is equal to k barred x prime square divided by barred y, and thus depends upon the depth at which the area is submerged. So here is the given figure in general, and we will call the distance from the center. We will call the distance from the differential element. So for our solution, we have a differential element dA here, and it is where the differential P acts, and the distance along the plane of the area to the water surface, that is to the liquid surface rather, that is exposed to the atmosphere, is y, so that the vertical distance from the liquid surface down to differential area, because this angle is also theta, and the figure is y sine of theta. So differential force is pressure at this level of differential area times vertical distance, and pressure at this level times differential area, and let's call that x, and this distance as x prime, and distance of dA from the x prime axis y prime as shown. So for the solution, differential P is pressure times dA, and pressure is equal to specific weight gamma times vertical distance y sine theta, then times dA. So putting constants, specific weight, and sine theta before the integral sign, and we note that the integral of y dA is simply area times barred y. Therefore, P is gamma sine theta times area times barred y. So we show first that P is gamma area barred y sine theta, or because barred y sine theta is the vertical distance of differential area from the liquid surface, and multiply it by specific weight, it's the pressure at the centroid of area, then multiplied by area, so it is also equal to P barred times area. So gamma area barred y sine theta, P is also equal to pressure at the centroid of area times area. Then for the value of x sub P, so moment about x-axis is P times yp equals integral of y times differential P by first moment of mass, where differential P is equal to gamma sine theta y dA. So therefore, putting gamma sine theta before the integral sign, so gamma sine theta times integral of y squared dA is the second moment of area with respect to the x-axis, and we will denote that by Ix. So again, integral of y times y dA is integral of y squared dA, that's Ix actually. So gamma area barred y sine theta, which is P times y sub P, equal to gamma sine theta Ix, cancelling out specific weight sine theta. Then we have left here area barred y, yp, then Ix. Therefore, y sub p or y sub cp is Ix over area times barred y, which we show that y sub p is really Ix over area barred y. Then my is p times x sub b, and it is equal to integral of x differential p, because the distance of differential area from the y-axis is x, then dp is equal to gamma sine theta y dA, integral of gamma sine theta y dA. So putting gamma and sine theta before the integral sign, then we have integral of xy dA. And integral of xy dA is the product of inertia of area with respect to the xy axis. So P times x sub b therefore equals gamma sine theta Ixy. So that's the product of inertia. Substitute the value of P, which is gamma times area barred y sine theta. So gamma area barred y sine theta equals x sub p equals gamma sine theta then times Ixy. We cancel specific weight sine theta again. So we have left here area barred y. X sub p equals Ixy. That's why x sub p is Ixy over area barred y. And finally, let's show that y sub p minus barred y is equal to this expression here. So y sub p minus barred y is equal to y sub p, which is Ix over area barred y, and minus barred y. Cross multiply, yp minus barred y equals Ix minus area barred y square over area barred y. So taking note that this Ix minus area barred y square is actually the moment of inertia with respect to the centroidal x prime axis, this one. So therefore y sub b minus barred y equals Ix prime over area barred y, or from this equation that by transfer formula for moment of inertia, Ix equals I barred x or Ix prime, I barred x prime plus area barred y square. So the distance between the x-axis and x prime axis is barred y, so that's why you have area barred y square. So that means I barred x prime is simply Ix minus area barred y square. So replacing this by I barred x prime, so yp minus barred y equals I barred x prime over area barred y. But I barred x prime is kx prime square, k barred x prime square times area. So yp minus barred y equals area kx prime barred square over area barred y, cancel out area. So we have also shown that barred y sub b minus barred y is k barred x prime square over barred y. And this equation is dependent on the depth because of barred y. And barred y is a function of the depth. So this equation depends upon the depth of submergence of area because of barred y. So that's it for this problem.